Hello everyone. Can you see my screen now? Okay. Okay. Hello and good day to all of you. To newcomer, I am Dr. Muhammad Azim from Dynaforming Engineering Technology, and today I will be presenting webinar. The title is Getting Started with the 3D Elasticity. Okay, for this topic, the target audience is a beginner in the Ansys mechanical. Okay, for those who are not familiar with the Ansys static structural, especially the newcomer, in general, it is an analysis tool for static structural analysis to determine the displacement, stress, strain, and force in structure or component caused by load that do not induce significant inertia and damping effect. Steady loading and response condition are assumed. That is the load and the structure response are assumed to vary very slowly with the respect of time. So so for today, we will review about the elasticity equation for the 3D component, and then type of finite element commonly used for the 3D stress analysis. The third one, we will study about several type of support, load and contact constraint. And then the lastly, we will do a demo for the predicting deformation and stress in the using Ansys workbench. So actually, why we do the structure analysis? So there are two reasons. So the first one is for the design, and the other one is the structure. So structural analysis is important because it can evaluate whether a specific structural design are able to withstand external and internal stress and force expected for the design. And then the second one, the reason is to determine the cause of the structural failure. Okay, as you can see now, structural analysis consists of the linear and non-linear behavior of the structural material. So for the linear, behavior, we assume that the material not physically deformed. Okay, and then for the non-linear behavior, consists of stress material past its elastic capability. Okay, elastic analysis calculate the effect of the steady loading condition on a structure while ignoring inertia and damping effect such as those caused by the time and varying load. Okay, so what we can say, the static have two conditions. The first one is the force is static, mean there are no variation with the time, and then the equilibrium condition for this force and moment is equal to 0. Okay, so before we start with the static structural analysis, we need to know lah why we perform the static structural analysis. So there are 5 reasons. The first one is the time, because the time to solve the nonlinear the solving process is relatively short. Okay, and then it's commonly used about 90% of time. The primary product we can understand the behavior of the product using the static linear analysis. And then this is for the initial study. Okay, before we do the nonlinear analysis, we can perform initial static analysis. And then for the linear static, we can understand the relationship between apply force and displacement. And then the last one is the linear case, where the stress remain in the linear elastic range of the used material can be understood. So so this is the application of the linear static. So we have many application that can solve many problems in aerospace, construction, automobile, offshore structure, sport, and so on. Okay, so before we start with the more deep, let's go to the elasticity equation. So elasticity equation consists of the strain and stress and strain. So from this, actually this is to follow the Hooke's law. If you and okay, it's follow the Hooke's law, so we can combine the stress and strain to get this equation lah. Stress equal to D. D is D and strain. So D is referred to the yaw modulus. So the overall equation can be presented in this equation below. So in the Ansys analysis mechanical study, actually we need two mechanical property, which is yaw modulus and Poisson ratio. This is very important because later we need to input in our analysis lah. Okay, so this is the process lah that we need to follow before we do the finite element analysis. So we start with the geometry and mesh, and then we go to the material. We need to define the material lah that we need, what material that we want to use. And then we need to also define the boundary and boundary condition and load. So after that, we go to the solution and processing. So as you know, we have many type of boundary condition, such as fixed support, frictionless support, and cylindrical support. So, okay, what is the fixed support? Fixed support is the actually prevent the geometry entity from moving or deforming. And then we have also frictionless support. Okay, frictionless support prevent the face geometry from moving or deforming in the normal direction relative to the face. And then we also have the cylindrical support. Okay, cylindrical support prevent the cylindrical face from moving or deforming in any combination radial, axial, and tangential direction. Okay, then we have another for the boundary condition, we need also to define a load. So the common load that we usually use is the force, moment, pressure, bearing, load, and so on lah. So and then we also have we also use initial load such as acceleration, standard earth gravity, or rotational velocity. And then other load such as thermal, electrical, and magnetic load. So the next is about the contact. So contact have 5 types of contact, which is a bond, non-separation, frictionless, rough, and frictional. So normally in the elastic study, we only usually we use 2 contact, which is a bond and non-separation. So this is the definition lah for each of the contact. So bonded is like a glue. So it's not allow separation and sliding. Okay, for the non-separation, actually it's not allow separation to occur, but it's allow sliding to occur. And then okay, this is the other. We will cover this later in the demonstration lah. So this is the what the summary for the contact. So as I mentioned before, so for bonded, it's not allow the separation. Separation means you cannot the gap and the gap for the between the contact must be cannot be closed. Okay, this is a summary lah for the contact. So from the final element analysis, actually we can obtain many results. So total and directional displacement, Mr. stress, normal stress, shear stress, bending, and so on lah. So this is the type of result that we can obtain from the Ansys simulation. Okay, so now I move to the demo. So we will do several demonstration lah for today. So this is the basic one lah. I think for the beginner must do this one, this simulation one. So we will cover several demonstration. Okay, so we start with this simulation. So so for to get started, you need basically build a 3D model or import a 3D model lah. Okay, so for now I already prepared my model. And then what you need to know is the load and boundary condition. And then what type of analysis that we want to do. So for now, for today, I already opened this one is a static structural. So for today we will do the static structural lah. Okay, so the first one, okay, you can actually from this workbench, you can drag the static structural and insert to the workbench. So as you can see, I already opened the analysis tab. So actually then this is called the project schematic lah. So actually this one you can name the title. So now I change the title to the test. Okay. For the current project, I call it the project is test. So basically, we won't go through each of these 7 component, which is engineering data, geometry, model, setup, solution, and result lah. To okay, now we go to the engineering data. Okay, this is actually where you choose all the type of material data. you are going to use for your analysis. So as you can see, we have the structural steel as the default material. Okay, and at the bottom, over here, you can see you can add another type of a material. Actually, to add another material, you just let's say I want to put the new material which is a stainless steel. So I just type the stainless steel. And then you can define the material property. So for example, for the stainless steel, you can select this one, isotropic elasticity, and drag to the stainless steel. So actually, normally, in this, we ask you to input this value, your modulus and Poisson ratio. So in order to use the stainless steel, you need to define lah what is the Young modulus and the Poisson ratio. So let's say the Young modulus for the stainless steel is first you need to define the unit. So maybe we use the megapascal. And then the Poisson ratio is 0.33. Okay, so another option, you can also go to the engineering data source, and then you can here have a library. This is a built-in library, so you can select whether Ansys, Granta, material, or so and so all lah. But for now, I want to go to the general material. So as you can see, now the outline of general material is appear. So here got many other materials such as uh, grey cast iron, magnesium, alloy, polyethylene, and so on lah. So you to select the material, you just click this plus, and then okay, now if you go back to the here, actually we have the another new add material lah. So now we have two type of material, which is the stainless steel and structural steel. Okay, so if you already satisfied with all the material here, you just can close the engineering data by clicking here. Just close lah. Okay, now so so now since this is a new model, so now we want to create our own model lah. So actually you can also import your own geometry. Okay, so the Ansys can you can import a file from for example from the SolidWorks or the STP file. Okay, but for now I just want to create a new geometry lah. Okay, so so I create a new geometry from the space claim. For the design modular. Actually, you can the new software for the Ansys is a space claim. But for now, I'm use design modular. So for the design modular, got two options here, sketching and modeling. So later we will sketch a new model lah. But before that, we need to go to the unit first. We want to check what unit that we want to use. Okay, for at the moment, I want to use the inch. Okay, so so now I move to the my axis to XY plane. So I click here. So for better, we need to define the grid by click the setting here. So you can check here to show the grid and also click snap here. So and then you can also define what is the spacing for the grid. So for this case, I use 1 inch lah. Okay, so now I want to draw the rectangle. Actually, this is for the cantilever beam. Okay, so I select the rectangle. Okay, and then so I already draw the rectangle. So and then actually then you can use the dimension to define the horizontal length. So now the horizontal length is 10 inch. So this is the length that I want to use. So and then after that I define the vertical length. So this is now the vertical length is 2.4 inch, but now I want to change to 3 inch. Okay. So basically I already done with the rectangular part. So but now I want to put I want to draw a cycle. I put in the I put here. So at the same step, I also can give a dimension lah for this circle. So let's say this one I change to 1 inch. Okay, it's now I want to specify the location for the cycle lah. So I click the center and here. So okay, so down done for the horizontal part and then center to this bottom. Okay, now I change to 1.5. So now it's already complete defined. So now I go to the model. So now I want to extrude this sketch. So I go to create and then click extrude. So for this model, so the dip I want to use is 2 inch. So okay. So the operation is to add material and then this is the important to define the width of the cantilever pin. So now I click here and then generate. So now the 3D model is already complete. Okay, so now we already complete our geometry. Now we can close the geometry. So now the next step is we go to the model lah. Okay, this is actually this is the basic lah for the beginner. So you need at least try once lah for this model. So as we discussed earlier, right? So now we need to go through one by one lah, from the geometry, material, mesh, and this one structural and so on. So now we already have the model. Okay. So actually in the previously we already defined the material. You can check. So we have two type of material here: the structural steel and stainless steel. So stainless steel is the one that we input. Okay, but the default material is the structural steel. Okay, okay, you can go here and select the solid body. So so at the moment our material is the structural steel. Actually, you can change the material into the other type of material lah. So this is a stainless steel, the material that we defined earlier. Okay, but I don't want to change the material lah. I stick to the structural steel. Okay. Okay. We go back to our problems, right? So now we want to define the this is a boundary condition lah. So the boundary condition. Okay. We can insert the fixed support. Okay. Let's say we input the fixed support at this the surface, and then we click the surface and then apply. So now we have one fixed support here, and then next we want to define the load lah. Okay, so for the load we can insert here. Actually got many type of load, such as pressure and force and so on. But now we use the we select force, and then here, and then okay, so now this one, right? Sorry. Okay, so now we want to apply the load to the x direction. So we need to change the vector to the component. So so the x component here is 200 lah. Okay. We actually we need to select the geometry surface. So we click here and then click the surface lah. So that means now you see we apply 200 Newton to the right. Okay, so now we already complete with the force and with the load and the support. Okay. Okay, now I want to go to the mesh. Okay, so as you can see here, the element size is already set as a default. So actually you can change the you can change the element size, but I think we skip that first. So if you click here, generate mesh, the mesh will appear lah. Okay, it will take a time to process lah, and then now the meshing is complete. You can see here is this is a mesh lah. At the moment, you can go to the static lah, static to see the number of node and element. So at this moment, you have only 2,298 node and 392 element. Actually, you can define your own element size. For example, let's say you reduce to you use this 0.5 inch. So sorry. Okay, actually this the unit is mm, but previously I used the in inch. Okay, so now I change to 0.5 inch lah. Okay, so you can click update or generate mesh again. So now the meshing will be refined lah. So the number of node increase and element increase, but also you can okay, actually to make this meshing more finer, you can increase the resolution. Okay, so this is the mesh lah that okay, actually here actually we already get a good mesh, so no need much editing. So now we need to define the what result that we want to obtain. For let's say we want to get the result for the deformation and also the stress equivalent vertices. So this is for equivalent stress. Actually, this for the ductile material. So now we already defined all. Now we can click solve to get the result. So this is the result that we obtained. Okay. So here we have two result. First is the total deformation, and then the equivalent stress. So this is the result for the total deformation. Actually, then you can get you can see the result in the tabular graph, or you can see the animation that generate. Okay, both is the same. Okay, now actually we already complete for this fundamental of the static analysis. So we will go through another type of study, demonstration. So okay, so I close this. Okay, so now we try to move to another example. So another example is about the pneumatic cylinder cover. Okay, so the objective here is to determine the circularity of the internal surface. Okay, so for this problem, actually I already defined the geometry. I already import the geometry. So now we just go to the model. So double click, and then the model will be appear. Okay, so for this study, we want to assess the circularity lah. Okay, actually this is the model for the pneumatic cylinder cover. Okay. So sorry for this. Actually, we need to define the material first. So to define the material, we go to engineering data. So so for this material that we want to use is the ABS. Okay, so the material is a ABS plastic. So now we drag the elastic elasticity here, and then okay, so now we need to input the jam modulus. So I input here is a 2.2 exponent 10 PA Pascal, and then the Poisson ratio is 0.3. So after we define the property, okay, actually for the we don't need to define the bulk ensure modulus because it's already automated calculated. After we input the Young modulus and Poisson ratio, the bulk modulus and shear modulus is will be generated lah automatically. Okay, so at the moment we no need to use the thermal load because it's not involved with our simulation. So if let's say our simulation involved with the thermal expansion, then it might be included lah. So now we already done with the define our material properties, then we can close lah the engineering data. So we go back to our model. Okay, so now we need to make sure that the unit that we use is correct. So now we use this unit in the metric. So mm, kg, newton, second, and so on. So we select this unit, and then now we want to use we want to use a ABS plastic to our material. So we want to change lah this our um, material from the structural steel to the ABS plastic. So now our material is the ABS plastic. Okay. Okay. So this is now we move to the mesh lah. Okay. So you can select generate mesh. So automatically this is the default meshing lah. So you can see here. This is the mesh. Okay, but you can so at the moment you have this one 11,000 node and 5,000 about 5,000 element. So and then actually you can change the mesh. You can change the number of mesh. Refine lah. So the same lah. You can this is the solution you can increase lah. Maybe you can use resolution about up to 4. Okay, and then generate again. So now you have, now you see here the number of mesh. Sorry, the number of node and element is increased. Now the number of node is up to 26k, and the number of element is 14k. Okay. Okay. The question is how to know that the mesh is the quality is good. Okay. You can go to this one, quality, and then you can at the moment this is you go to the mesh metric. At the moment the mesh metric is none, but you can select the element quality. Okay. So for the element quality, you must obtain about okay. So this is the element quality lah here. So the majority of the element here is more than 0.25. So what can you say? We have a good element. So only a small number is less than 0.2. So for this element quality is acceptable. Okay, so now I think we have no problem with the meshing lah. So now we need to define our boundary condition. Okay, so now okay, so okay, so now we define our boundary condition. So we want this problem we use the frictionless support. So for the frictionless support we will select this space for this frictionless support. Control select, and so so the total number of phase is 12. So we select all this phase as the frictionless support. So and then after so make sure we select all the 12 phase here, and then we click apply. So now we have a frictionless support here. Okay. Okay. The next one we want to define the pressure. So the pressure reduce at the center, and then to all this phase. So on overall, we have about 39 phase. So now we already select the phase that we explain the pressure. So now we apply the phase. So all this phase will explain about 0.5 megapascal. Okay. So for the solution, we will select the total deformation. And then we want to study about the equivalent bond misses. And also we will select this error. So now we have defined all the support, boundary condition, and solution. Now we can solve the problem lah. So this is the solution. Okay, but actually but we want to actually we want to determine the cylindrical to assess the circularity. So we need to come up with a new coordinate because we want to determine the actually we want to determine the deformation in this area in the surface. So what we need to do now is to create a cylindrical coordinate system. So insert the coordinate system. And then so now the type is a Cartesian. So now we want to change to the cylindrical. Okay, geometry is we select so for geometry we just apply. So now you can see now we already changed to the Cartesian to the cylindrical coordinate system. So for the coordinate system, so you can see we have in the Cartesian we use x, y, z for the coordinate axis, but now the coordinate is now interpret as the radial, theta, and z. So now we want to access this circularity. So we now so for the geometry we select this face and then apply. So we change the coordinate system now from the global coordinate system to the the new one that we set up here. Okay. Then after that we can evaluate to obtain the result lah. Okay, so now we get the deformation for the at this surface. Okay, now we done with the this demonstration. So I close. Okay, for the next one, it's about the contact. Okay, so this is another model lah. So as you can see, this is assembly model. So this is model consists of 3 components, which is this is the Y shape. Here is a yoke, and then you have a U shape, and then the third component is a pin. So every assembly will contain the contact lah. So how to check the contact? Actually, you can go here connection, and then go to the contact. You can see here you have a 3 type of contact lah. Okay. So the contact you can be thought as a skin lah, covering the surface that expected to interact with one another. Okay. So for the contact you have two surface lah. So for this one, the red one is the contact body, and then the blue one is the target body. Okay. So for the contact, right? The Ansys we define the type as the bonded lah. Okay. But okay, the bonded mean no separation occur and then no sliding occur. So we want to change the bonded to the no separation lah. So because we not allow the separation occur, but we only allow the sliding to occur. So we change all the bonded to the no separation. Okay, so the S actually is the advanced setting lah. So we need to do that. So the material, all the material is the structural steel. We only use the structural steel for this study. So and then we can generate the mesh lah here. Okay, now we can check the mesh lah. Okay, so actually we can, for the mesh, right, we can use the refine to get a better meshing condition for this pin lah, because this pin is the most affected area. So then I select body here and then click apply. So for this for pin, I select for face, and then I generate again lah to produce a better machine for the pin. So now we can check lah the mesh. So this pin has a better machine lah compared to the other. So that the number of node and element is increased, so that we can get a better accurate result for the pin. So now we define the boundary condition. So we insert the fixed support here and apply, and then we put the another load, which is a pressure here at the surface. Then let's say I put the load here is 1 megapascal. So now we want to get the deformation total, and then stress for misses, stress, and then another option we can insert this contact tool. Okay. This one because we want later we want to determine the behavior of the contact region. Now we can click solve to solve the problem. So it will take some time to solve the problem. Okay, so now we already get the result. So this is what happened to our problem. So but actually the total deformation and equivalent stress is similar from the previous one. But now what we interest is uh, the what happened at the contact. So you can see here uh, mostly our model here is to explain the sliding due to the pressure that we applied before. So this is what happened actually to the our model. So majority type of the type the contact explain the sliding. Okay, so this example show what is the importance of the contact. Okay, so now we done. So actually we already done our third model. So now we move to the last one, the last model. So this one actually to show you that we can reduce in. Okay, so this is the last example lah for today. So this is a flywheel lah. Okay, so the objective for this analysis to demonstrate lah the process using the symmetry. So it's so it take time. Okay, so this is our model of flywheel. So for this model, I will put the fixed support here. Sorry. We put the fixed support at this surface. Okay, and then apply, and then again the flywheel is rotated at some speed. Okay, and then we need to define the rotational velocity. So the rotational velocity here, but is we need to define the rotational velocity by the components lah. So this is so basically the rotation occur at the y axis. So let's say we put the speed of the velocity is 100. Yeah, and then we want to know the directional. So since it's rotational occur at the x-axis, so we can call it as we can name it as the radial directional deformation, and then also we can find the formations lah. So I didn't change the type of material and so on. So then I click I solve the problem lah. Okay, so this is the result. Okay, but actually I want to show you that we can use reduce the here the number of mesh and element is 2030 336, and the element is about 1000. Okay, but we can also reduce the model. We can simplify the model and obtain the similar result. So I close now and then go to the another. Okay, I make a modification lah. So now I open the geometry in the design modeler. Okay, we take some time to load the geometry. Okay, so now here is our model. So okay, so as you notice, this is symmetry. This model is a symmetry. So you can reduce the surface for this element. So how to reduce the surface? Actually, you can click tool and select the symmetry. Okay, so now we want to cut the model in the XY plane. So then now we can select apply. Okay, so now we can generate here. So now now the model is reduced to half. Okay, so now our model is still symmetry. We still can cut model into half. So we click symmetry, and then at this now we select the XY plane. Okay, and then click apply. So then generate. So now is the simplified model lah. Okay, so this is the now we cannot cut anymore. So this is a reducer model. So now we close and open uh, in the model lah. Okay. Now I go to the model. Okay, so this is our model now. So it's already okay. Now you can see here got the you can see here is the symmetry. So actually our model is not we only reduce our model to the this part only. Okay, so if you generate the mesh, you can see here the number of nodes is reduced compared the previous one. So actually, if you define the boundary condition and load, actually you get the same result lah. So for this one, fit support, click the surface and apply. And then for the load it is rotational velocity same. So this one at the y direction. So I assume is 100 radius per second. Okay, so the main purpose to reduce the model actually to get to reduce the time lah for the simulation time, and then to save processing to get a better result lah. So if we compare with the previous result, actually the result is almost similar lah. Okay, I think so I open for the question. So I am done with all the demonstration. So now we already 5:10 p.m. So I think I done with all the demonstration. So I open with the Q&A session.
Thank you very much, Dr. Azim. Before we move to Q&A session, I will launch a poll. Please select the appropriate response and click submit. Now Dr. Azim will answer question. Actually, we are running out of time. Maybe we can have one question before we end this session. So anyone have question regarding this webinar?
Hi.
No. Okay, if not,
Hear me? Hello.
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 Sir,
Hi.
okay.
Hi. Yeah. Hi. Just want to ask, right? Sorry. Just now with regards to the pressure at Mr. Hazim, if you select the faces like that, right, for pressure, does that mean it would it would apply the pressure on a direction perpendicular to the surface you're applying to? So if you are applying to two different surfaces on different sides, does that mean the pressure would cancel each other out?
Sorry. Okay.
So yeah, that was just what I was wondering. So if you apply, for instance, on the same wall, but since the wall is 3D, right, that means you apply on the left hand side and the right hand side on the same wall. Does that mean the pressures cancel each other out, or how does that work?
Okay, actually it's not cancel each other lah. Actually now if you apply the different pressure, so you have two boundary condition lah. So it's depend lah. So so the pressure that you apply have the similar different value or different component direction component lah. It's depend on the direction and the value. So if even though he have the same direction, the Ansys we define it as a two. Now you have a two boundary condition lah.
I see.
So
So it's not canceling each other out, right?
So it's not cancel each other.
Or even though the magnitude is the same, it doesn't mean it's
Uh,
cancel each other out, right?
Yeah.
Okay. Okay. Thank you.
Okay, we have, anyone have another question? Okay, it looks like we have covered all of our question. Thank you again, Dr. Hazim, for answering the question. Dr. Hazim, is there anything else you want to cover?
So actually, you can go to our Facebook and LinkedIn for more question. And then I hope you can like the Facebook page and then you can suggest a new topic lah for the next webinar.
Great. Before we end, I would love to share with you about our upcoming event, which is Level Up 3.0. This event we will conduct on 25 October. Be sure to mark your calendar to save the date. And we encourage you to connect with us on social media to get the latest information. You also can contact us by email or telephone. We are happy to provide additional support. Thank you all for attending. We hope you have learned and enjoyed this presentation. Have a nice day. Thank you.
Thank you.